You may have noticed up to this point that we have taught you some algorithms or processes for doing the process of integration, but we haven't done a large amount of explanation about what an integral is. And so some of that is we need to lay some groundwork for this. So we're going to start with this idea of what's called sigma notation. So sigma is this Greek letter, and when we use this notation mathematically, what we're indicating is a process of addition. Right? So anytime you see sigma notation, really it's a signal that we're adding a bunch of things up. Right? More specifically, when we use sigma notation, we'll have a couple different things. We might have a statement like this. The I isn't important, but it's just denoting something. So it's saying I equals 1 to some number n, a sub I. The I itself is called the index of summation, and that's just telling you something about the term numbers that we will be adding up. So this is starting with a term number of 1 and ending with a term number of n. And a sub I is a rule, so to speak, to generate any of the terms in the sequence. So this represents, our first term would be a sub 1, our second term would be a sub 2, and we would keep going until we had a sub n minus 1 and finally a sub n. This will make some more sense as you see some examples. But the biggest thing is that sigma notation is a way to write out large addition problems, and we still would need to calculate the sums ourselves. So let's look at some basic examples. We're going to take the sum from I equals 1 to 8, and our rule is 3. So what this means is that we're adding up, there's term number 1, 3, and the rule is the same for every term. So there's term number 2, term number 3, number 4, number 5, number 6, number 7, and number 8. And so the sum is 24. So we have 3 different ways of expressing this sum. So that's what that means. Let's consider a different example where we have a rule rather than just a number to deal with. So here we have the summation from I equals 1 to 6, and the rule is I. So that means I'm going to start with the number 1 and substitute in for I and have 1. My second term will be the next number for I, 2. My third term will be the next number for I, 3. And I'm going to keep progressing this way until I get to my last number, which will be 6. And the sum of these 6 numbers is, so 11 plus 7 is 18, 18 plus 3 is 21. Let's consider 2 more examples. Third example, the summation is j goes from 1 to 7 and the rule will be j squared. So this means we're going to start with 1 and square it, and our next term will be 2 and square it. We're going to keep going in this way until we get to 7 squared. And now we just need to find the sum of these numbers. And although a calculator would be nice, it really isn't necessary at this point. We can still do this for the most part ourselves. And when you add each of these terms up, you will end up with, let's see, 140. Our final process for the summation, let's so you have something slightly different. So this is, the sum is k, goes from -2, so that'll be our first value of k, to 3, that'll be our last value of k. And our indexes, which is what k is in this case, are always just increasing by the integer numbers. The rule will be k cubed. So that means in this case we'll be looking at -2 cubed plus -1 cubed plus 0 cubed all the way to 3 cubed. And again, we don't need a calculator for this. -8 minus 1 plus 0 plus 1 plus 8 plus 27. And the sum of this is simply 27. There's a few examples of some basic summation problems. There are two rules that I'd like to talk about, or two properties of this that we can apply to any summation problem, and then we'll look at some more examples in part 2 of this. So any summation problem is just an addition problem. So since it's just an addition problem, then basic properties of addition and multiplication do apply. If we have a rule that's being multiplied by a constant, we do have the option of factoring that constant out. So this is equal to the constant times the sum of whatever these numbers would be. The second thing that you're allowed to do is, let's say you have a more complicated rule, I equals 1 to n, and it might be some rule I plus or minus some second rule in terms of I. You could consider each piece independently. That means you could find the sum of everything for just AI, and then once you're done, add or subtract it to the sum of just BI. Right? I don't have to do the whole thing together. I can write one sum as two sums. And so with these in mind, let's consider a few more examples. We've got this, here we have the sum as I goes from 1 to 7 of 8i, and I'm going to apply the rule that allows me to factor out that constant, so this will become 8 times the sum as I goes from 1 to 7 of just I. This means that I will have 8 times 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. And since the directions have told me I'm allowed to use a calculator on this, I will. And when I do, I end up with 224. Now for example 6, what we have is the sum as I goes from 1 to 5, and the rule is 5i minus 2. So I'm going to apply the second property and break this up into two sums. The first is the sum as I goes from 1 to 5 of just 5i, and that will be minus the sum as I goes from 1 to 5 of 2. Well, our first sum will be 5 times 1 plus 2 plus 3 plus 4 plus 5. And then that we'll have subtracted from it the sum of -2, not once, not twice, not 3 times, not 4 times, but 5 times. And when I simplify this down, I end up with 85. So there's some application of our properties. In the next section, we will consider a few more examples involving sigma notation, and we'll go from there.